We are Team Zebra Blitz, and our project is energy harvesting to power a patient tracking Bluetooth angle of arrival locator. Our sponsoring company is Zebra Technologies, and they are headquartered here in Lincoln, Rhode Island. Zebra is a company that provides a wide range of products and services across retail, healthcare, transportation, and logistics, and other industries. These technologies are used to intelligently track people, connect people, assets, and data. We are led by Timothy Vermilia, the systems engineer, Dave Teal, the principal software engineer, and Jamie Gagnon, our consulting technical director. The URI team includes myself, Fatima Lynch-Smith, an electrical engineer, Alexis Estrada, a computer engineer, and Kashmir Ryan, also an electrical engineer. There are currently patient tracking systems available on the market. However, these systems are expensive and take excessive amounts of time to install due to the wired design. They also continuously draw energy from the power grid, raising electricity costs. Our project revolves around designing a blitz locator that will track patients in various healthcare settings with 99% accuracy. These devices will reduce cost of materials and labor and will be installed in under 2 minutes without any wiring. The Blitz locator will be powered by ambient light using photovoltaic cells to harvest low light in minimal conditions. The anticipated best outcome of this project is to conduct rigorous research and analysis of cutting-edge photovoltaic technology and select our top 2 vendors for the Blitz locator system. The Blitz locator is a device that will be scattered throughout a hospital environment and use complex angle of arrival algorithms to track patients wearing wristbands. To describe our progress and timeline for this project, we will use a process pyramid. A PV cell is a semiconductor material, usually silicon, that is used to collect light energy and convert it into electricity. When talking about low light levels such as indoor light, a measurement known as lux is used to measure the light intensity. I have researched several types of PV cells such as organic photovoltaics, amorphous silicon, polycrystalline, monocrystalline silicon, and photovoltaic ink cells. All of these types of PV cells have their own efficiencies, advantages, and disadvantages. My work consisted of collecting data from specification sheets from various indoor photovoltaic cell manufacturers. I then contacted those manufacturers for development kits so that we could test their compatibility with our design. I also defined a method to simulate the PV cells in LT-SPICE. Our next presenter, Alexis Estrada, will explain in more detail the next phase of the process pyramid.
Thank you, Fatima. Now that we have a base understanding of how PV cells function, our next step was to understand the environment that the Blitz locator will be operating in. In our case, it is a hospital setting. Doctors and nurses are directly responsible for the safety and life of their patients, so there can be no room for error or second guessing what they are seeing on a day-to-day basis. Lighting conditions in hospitals are strict due to the nature of work being performed. In our research, we found that there are various public, private, regulatory, and voluntary initiatives that dictate hospital standards. One such organization is the Occupational Safety and Health Administration, also known as OSHA. Many of the lighting standards we found all fell within a typical range for each different type of room. Here are some of the values we expected in different areas. Keep in mind that direct sunlight is approximately 50,000 lux, and we are dealing with only a small fraction of this level. The locator device will need to be able to harvest lighting from any of these conditions. Our next step was to gather live data within a hospital to verify that our research values hold true. But before we could do that, we had to dive into selecting a lux meter that could handle ambient lighting and record data effectively. We decided on 2 separate devices, one of which is a handheld meter that can be used to find an optimal or insufficient lighting location within an area at an instance, and another that could collect and store light levels at different times of day by mounting it in a desired location. After concluding our final selection, we ordered them and took a visit to a local hospital to take measurements. Our findings showed that the hospital was following appropriate guidelines because our measured lux values did in fact match or exceed our expected conditions based on our research. This information is valuable because it will be used to determine how we test and select our desired PV cells. Our next presenter, Casimir Ryan, will explain this information in more detail.
Thank you, Alex. As my two partners have explained, we've done a considerable amount of research and data collection up to this point. But you may ask yourself, what are we actually doing with this data? Where I spent a considerable amount of my time was creating test fixtures for our panels. As you can see here, the first housing that we made for the panels is our solar simulator. The idea here is quite simple. A 3D printed box, a light bulb socket, and a voltage regulator to control the brightness of the bulb in the housing. But how does this work together? First, we take one of our light meters, stick it inside of the box, then close it up and adjust the brightness of the bulbs using the regulator to match the same level of lux that we saw in the hospitals. Once this step is complete, we will take out the lux meter, insert a panel, and begin testing its efficiencies. However, these photovoltaic cells aren't efficient if they aren't placed at the correct angle, and as you saw at the beginning of the presentation, these units will be mounted on the ceiling. This is where our PV angler comes into play. We will test in the range of 25 to 50 degrees in increments of 5. The 6 different fixtures will then be placed on the ceiling using a magnet, and we will be able to figure out the most optimal orientation for our test prototype. This directly leads us into the top of our pyramid, our deliverables. What's next for us? First off, we need to receive the remaining development kits. We'll need to use our test fixtures to actually analyze each vendor that we've had and see what they have to offer. Once this is done, we can then narrow down to our top 2 contenders and create a prototype for a ceiling and wall mounted fixture based off of those findings. Let's take a quick look at the broader implications if we are successful in increasing the battery life of our locator. From an energy efficiency standpoint, we will be taking pre-existing units off of the power grid, creating a greener environment. From a company and industry perspective, Zebra will be able to bring the only turnkey solution to an emerging market that excludes the extensive installation period, which puts it leaps and bounds over their competitors. And this concludes our presentation. Thank you.